So good afternoon all of you. So in this lecture we will discuss the pseudo random number generators. So random numbers have many use in cryptographic algorithms. So cryptographic applications typically make use of algorithmic techniques for random number generations, and these algorithms are deterministic and therefore produce a sequence of numbers that are not statistically random. Some of the application areas of these random numbers are to generate nonces in authentication protocol to prevent delay, so that we have seen in our earlier lectures that nonces are used for authentication protocols. Then to generate session keys whenever the two parties want to communicate with each other. Then during that communication, the certain session keys that are generated, they are based on random numbers. Then for public key encryption algorithms like the RSA algorithm, and also for the key stream for one-time pad that we have seen in case of block cipher modes of operation. And in all these applications, it is critical that the value should be random. So random means that they should be statistically random, they should be uniformly distributed and independent of each other. Along with it, it should be unpredictable to predict the future values based on the previous values. So these algorithms that are used to generate random numbers, they are often deterministic. So although they are not truly random, they can pass many tests of randomness. So we will see what are the different tests of randomness. So the numbers generated by such algorithms are known as pseudo random numbers, and these algorithms are known as pseudo random number generators, that is PRNGs. So in this lecture we will see some of the different techniques that are based on pseudo random number generators. The first method is linear congruential generators. So this technique is basically based on iterative approach, given as that the next random number, that is xn plus 1, is equal to axn plus c mod m, where x naught is basically the start value or the seed value, a is known as the multiplier, b is the increment, and m is the modulus. So given a suitable values of parameters, we can produce a long range of random like values. So what are the different criteria that these pseudo linear congruential generators should satisfy? So basically there are three tests denoted as this is known as test T1, this is test T2, and this is test T3. So the first test is that the function should generate a full period. So that means that the function should generate all the random numbers between 0 to m and before start repetitions. Okay. Second test is that it should generate sequence that should appear random. So it should not be that there should be particular sequence among the numbers generated. They should appear that the numbers generated are completely random. And the third test is that it should be efficient implement on a 32-bit architecture or the 32-bit arithmetic operations. Now it must be noted that the attacker can reconstruct sequences given a smaller number of values. So in order to make it harder for the attacker, the value of m should be very large. So once the value of m is very large, then it is difficult for the attacker to generate these random sequence. So let us take an example. So let this congruential function or this iterative function is defined like this, that xn is equal to 3xn plus 5 mod 31. So a is 3, b is 5, and m is 31. And we have taken the initial seed x naught equal to 2. So here 3 and 31 are relatively prime, and 31 is prime, that is of order 30. So using this iterative functions, we can generate 30 residues in this cycle given by this. So as you can see that this is a random sequence, and it contains the full range of residues, and that is from 0 to 30. So similarly, we can generate a pseudo random number sequence of 10 bits. So by taking x naught equal to 2, we can generate such a series of random bits, and by taking x naught equal to 3, we can generate another sequence of random bits. So the second method is using block ciphers as pseudo random number generators. So for cryptographic applications, we can use block cipher modes of operation to generate random numbers. So often these are used for creating session keys from a master key. So as we have seen, like in the AES algorithm or the DES algorithm, we have one master key, and from that master key we can generate multiple session keys. So in such operations, we can use these block ciphers as the pseudo random number generators. And for this, generally we use two modes. Either we can use a counter mode given by this, or we can use output feedback mode given by this equation. Okay, so using either of these two modes, we can generate block ciphers. We can use block ciphers as pseudo random number generators. So third mode of pseudo random number generation is Blum-Blum Shub generator, and that is known as the BBS generator. So let us first understand the concept of BBS generator. So this BBS generator is based on quadratic residues. What are these quadratic residues? So let us assume that P be an odd prime and A be an integer. So we say that or we define as A is a quadratic residue modulo P if A is not congruent to 0 mod P, and there exists an integer x such that A is congruent to x square mod P. And the opposite of is that A is a quadratic non-residue modulo P if A is not congruent to 0 mod P and A is not a quadratic residue to modulo P. So let us understand this concept with the help of an example. Suppose this P is a prime number, P equal to 5, and then we can see that 1 square is equal to 1 in terms of mod P. 2 square equal to 4, 3 square equal to 4, and 4 square is also equal to 1. So how we have computed that 1 square equal to 1 mod 5, this is equal to 1. 2 square is equal to 4 mod 5, so this is equal to 4. Then 3 square equal to 9 mod 5, this is equal to 4, and 4 square equal to 16 mod 5, this is equal to 1. So in this manner we have computed the quadratic residues. So from this we can see that 1 and 4 are the quadratic residue of modulo 5, while 2 and 3 are not quadratic residues to modulo 5. Why? Because we can see that for 2 and 3 we get the quadratic residue as 4 and 4. Okay, so this is the basic concept of a BBS generator. Now let us see the algorithm that is used by the BBS generator. So this BBS generator is based on squaring one-way function. So if you remember what is one-way function, that given x, it is easy to compute f of x, and this is easy to compute. However, computing f inverse of x is very difficult or almost impossible. So this is the definition of one-way function. So what is the algorithm? So let P and Q be two odd primes such that P is congruent to 3 mod 4 and Q is also congruent to 3 mod 4. Let n is equal to P into Q, and let x naught be the seed, which is the quadratic residue modulo n. Okay, then the BBS generator produces a sequence of bits according to the following algorithm, that xi, the next bit, is equal to xi square mod n. Okay, so the output will be a sequence of bits, so yi equal to x mod 2, so this will be the sequence of bits. So y1, y2 up to yk, this will be a pseudo random sequence of k bits. So in this manner the BBS generator algorithm will work. Coming to the security of the BBS algorithm, so the output that is generated by the BBS algorithm should pass the next bit test. So what is this next bit test? So a pseudo random number bit generator is said to pass the next bit test if there is a no polynomial time algorithm that on the input of the first k bits of the output sequence can predict the k plus 1th bit with probability significantly greater than 1/2. So if the output passes this test, then we say that it passes the next bit test. And generally this security lies on the difficulty of factoring n, so that we have seen that n is equal to p into q, with both p and q are odd prime numbers. So the entire security of this algorithm depends upon the factoring of n into 2 odd prime numbers. So it should be unpredictable given any run of bits. So if suppose we have given any sequence of bits, so by looking at the sequence of bits, it should not be possible to predict the value of n and p or q. However, this algorithm is very slow since very large numbers must be used. So these two p and q, they should be very large for the security, but this makes the entire algorithm very slow. And as well as it is very slow for cipher use, but it is only used for key generation purpose. So this was all about the Blum-Blum generator. Finally, we will see how we can use the natural sources as the generator of random noise. So the best way to generate random numbers is to use a natural randomness that is present in the real world. So what we can do, we can find a regular but random event and a monitor. So such as your pulse generators in the ionizing radiation events, or the gas discharge tubes, or the leaky capacitors. So such kind of sources we can use, and for them we do not need any special hardware, and all such sources can generate the true random numbers. And in the modern CPUs we could find such kind of sources to generate random numbers. However, there is a problem of bias or uneven distribution in the signals. So it may be possible that the output generated by these sources could be biased. So we have to compensate for this when sample and use, and the best way is to use only the few noisiest bits for each samples. So in this manner we could overcome the problem of bias. So this is all about the pseudo random number generators. Thank you.